Hi, Dr. Jonathan Chamberlain, and this is Exploiting Kubernetes Autoscaling for Economic Denial Sustainability. This is work I did at Boston University alongside undergraduate lab assistant Jillian Zhang, my thesis advisor, Professor David Sarobinski, and our collaborators at Maryland, PhD student Zhang Zhu, and Professor Xiaojing Liu. So with Kubernetes, we have the ability to have flexible demand response in response to changes in traffic, whether that's increasing or decreasing the amount of replicas. And so cloud applications build on top of this in order to create an ecosystem where they only pay for the computing resources that they require at any given instance. But this can be exploited by adversaries to create an economic denial sustainability scenario where an adversary can show up and create excessive amounts of traffic, in turn creating excessive amounts of replicas, causing the application to go bankrupt, making it go offline, and angering the customers. And so the questions that we want to answer revolve around how do we formalize these scenarios? What are the circumstances that cause this to potentially occur? And so we model these using Markov decision processes, which are defined by the state space's available actions, and the objective functions. So for the defending application, the states are the number of service units active and the number of requests currently in the system, and they can either add or remove a service unit or keep them the same. And their objective is to minimize their total cost based on both the cost to actually operate the service units as well as service level agreements related to the number of requests currently in the system. And so at any given state, when an arrival or departure occurs, the application must decide whether it needs to adjust the level of service units in order to optimize that trade-off between the SU cost and the SLA violations. And the decisions made at each state will determine the overall policy, which optimizes the operating costs. Now, for the attacker, they are building off of the state space solution determined by the defender, and they're trying to determine whether to remain idle or send traffic at some rate higher than the legitimate arrivals, with the objective of maximizing the defender costs while minimizing their own. So the attacker wins if they spend less than the defender does. So, with the attacker present, an arrival can occur at the standard rate, or it can occur at an elevated rate due to an attack being in progress. But ultimately, we don't visit states that we wouldn't have otherwise because the attacker is working from the existing policy and isn't trying to induce new configurations. However, building off of what we know from the MDPs and running experiments, we find that while indeed, if you send greater amounts of traffic, you're going to create a larger number of service units, you also see diminishing returns when trying to run the attack, in the sense that just because you create more service units doesn't mean you're creating them at the same rate that you're sending the additional traffic. Sending traffic at 20 times the amount of the base traffic rate, for instance, doesn't mean you're going to get 20 times as many service units to generate. And so the full details are contained in our paper, but using these models, we find that the viability of attacks depends on how you charge for the service units and the potential for service level agreement violations to occur more frequently the more constrained the environment is. And we also propose countermeasures in the form of scaling randomization within the paper itself. The idea being to disrupt the assumption on the attacker's part by making the policy non-deterministic.